The Singleton pattern is one of the original creational design patterns described in the Gang of Four's seminal design patterns book. At its core, Singleton makes a simple but powerful promise. It guarantees that a class has exactly one instance, and it provides a global point of access to that instance. This is fundamentally different from other creational patterns. Instead of helping you create varied objects, Singleton restricts creation to ensure exclusivity. In this deck, we'll explore what Singleton is, why it exists, how to implement it correctly across languages, and, critically, when to avoid it. Understanding both its elegance and its pitfalls is essential for any software developer working with shared resources and global state. So what exactly is a singleton? At its simplest, it's a creational design pattern that ensures a class can only ever have one instance, and it gives you a global way to access that single instance. Think of it like the president of a country. There can only be one at any given time. Everyone knows how to reach the office, and nobody else can just declare themselves president while the position is filled. The first characteristic, single instance, means that no matter how many times your code requests the object, it always gets the same one. Global access means there's a well-known entry point, typically a static method like getInstance, that any part of your codebase can call. And the private constructor is the enforcement mechanism. By hiding the constructor, the class prevents any external code from creating additional instances, making the singleton the sole gatekeeper of its own creation. Let's paint the picture of what goes wrong without singleton. Suppose you have 5 different modules in your application, and each one independently creates its own database connection. That's 5 separate connection objects, each consuming memory, each potentially holding different configuration or state, and each competing for the same database server resources. You get wasted memory from duplicate objects, inconsistent state because each connection might have different settings, and resource conflicts where too many connections overwhelm the server. Now contrast that with the singleton approach. When you call database connection, getInstance 5 times, you always get back the exact same object, one connection, one configuration, one pool of resources shared by everyone. This is especially critical for shared resources like database connections, loggers, and configuration managers, where duplication isn't just wasteful, it's actively harmful. Let's walk through the classic lazy initialization implementation line by line. First, we declare a private static variable called instance. This holds our single object and starts as null. Next, we make the constructor private. This is the key enforcement mechanism that prevents any external code from calling new singleton. Then we have the public static getInstance method, which is the global access point. Inside, we check if instance is null. If it is, we create the one and only object. On subsequent calls, instance is no longer null, so we simply return the existing one. This is elegantly simple, but there's a critical flaw. In a multi-threaded environment, 2 threads could both see instance as null at the same time, and both could create separate instances, defeating the entire purpose of singleton. We'll fix this in the next slide with thread-safe approaches. Let's compare the 2 main approaches to making singleton thread-safe. On the left, we have double-checked locking, the classic technique that uses a volatile field and synchronized block to ensure only one instance is created even when multiple threads call getInstance simultaneously. The volatile keyword is critical here. Without it, the JVM may reorder instructions and allow a partially constructed object to be visible to other threads. The 2 null checks reduce the performance overhead of synchronization after the instance is created. On the right, the enum singleton is Joshua Bloch's recommended approach from Effective Java. It's dramatically simpler. The JVM guarantees that each enum constant is instantiated exactly once, and it's inherently thread-safe. More importantly, it automatically defends against serialization attacks and reflection-based instantiation, which the double-check locking approach does not handle out of the box. For most Java applications, the enum approach is the best choice unless you need lazy initialization or your singleton must extend a class rather than implement an interface. Now let's see how the singleton pattern adapts across 3 major programming languages. Python offers a unique advantage. Its module system makes explicit singletons often unnecessary. Since a module is only loaded once by the Python interpreter, any object defined at the module level is effectively a singleton. But if you need a class-based approach, overriding __new__ lets you control instantiation, as shown here. C# takes a different path with its lazy generic class. This is a beautifully elegant solution. Lazy automatically handles thread-safe lazy initialization, so you get all the benefits of double-checked locking without writing any synchronization code yourself. The sealed keyword prevents subclassing, and the private constructor prevents external instantiation. In Java, the enum approach we saw earlier remains the gold standard. With just 3 lines of code, public enum singleton with instance, you get thread safety, serialization safety, and reflection safety, all guaranteed by the JVM. The key takeaway is that each language has idiomatic features that shape how the singleton is best implemented. The pattern stays the same, but the expression adapts to the platform's strengths. Let's walk through the 4 most common real-world scenarios where singleton is genuinely the right design choice. First, the logger. Virtually every production application needs a centralized logging service. Without a singleton, different modules might create their own loggers, writing to different files with different formats and timestamps, making debugging a nightmare. A single logger instance ensures consistent, unified output. Second, the configuration manager. When your app starts, it reads settings from a file, environment variables, or a remote service. You want this done exactly once, and every component should reference the same loaded configuration. Multiple config readers could load stale or inconsistent values. Third, the connection pool. Databases have finite connection limits. If every service class opens its own connections, you'll quickly exhaust the pool. A singleton connection pool manages a shared set of connections efficiently. Finally, the cache manager. An in-memory cache must be consistent across all components. If 2 modules cache the same data independently, you get duplicate entries, wasted memory, and stale reads. A singleton cache provides a single source of truth. In all 4 cases, the common thread is a shared, coordinated resource that must have exactly one manager. Singletons come with significant drawbacks that every developer should understand. First, hidden dependencies. When a class reaches for a singleton internally, the dependency isn't visible in its constructor or method signatures. This makes the code harder to reason about and refactor. You won't know a class depends on the singleton until you read its implementation. Second, testing becomes a nightmare because singletons carry mutable state across test runs. If one test modifies the singleton, the next test starts with polluted state, leading to flaky or silently broken tests. Mocking a singleton requires hacky workarounds like reflection or special testing libraries. Third, singletons violate the single responsibility principle by managing both their own life cycle and their business logic. These 2 concerns should be separated. The practical rule of thumb: if you find yourself needing to pass the object as a parameter, you probably don't need a singleton at all. When singleton causes more problems than it solves, 2 modern alternatives stand out. Dependency injection is the most recommended replacement. Instead of having a class reach globally for a singleton, you pass the shared object through the constructor. This makes the dependency explicit. It's right there in the signature, which means it's easy to see, easy to mock for testing, and easy to swap implementations. The code shows an order service that receives a logger via its constructor, making the dependency transparent. On the other side, the monostate or board pattern takes a different approach. It allows multiple instances to be created normally, but all instances share the same underlying static state. So calling setState on any instance affects all of them. The API feels like regular objects, but the behavior is singleton-like. The trade-off is that monostate still carries hidden state coupling, while dependency injection makes everything explicit and is generally the preferred approach in modern codebases. Let's recap the 5 key takeaways from this deck. First, Singleton guarantees one instance with global access. That's its core promise. and it's genuinely useful for truly shared resources like loggers, connection pools, and configuration managers. Second, while lazy initialization is the simplest approach, it's not thread-safe. In Java, prefer the enum approach, and in C#, use lazy of T for guaranteed thread safety. Third, every language has idiomatic ways to implement singleton. Python modules are naturally singletons, C# has lazy of T, and Java's enum is the canonical approach, so always adapt to the platform. Fourth, avoid using singleton just for convenience. The hidden dependencies and testing pain are real costs that compound over time. Fifth, when you need shared behavior but want to avoid global state, dependency injection is the modern best practice. Thank you for your attention. I'd love to hear your questions and discuss your real-world experiences with the Singleton pattern. The Gang of Four book is where it all began. The original 1994 catalog that formally defined the Singleton pattern alongside 22 other design patterns. Joshua Bloch's Effective Java is the authoritative modern source, particularly Item 3, which recommends the enum approach as the best way to implement a singleton in Java. Refactoring. Guru offers one of the best visual and practical references online, with clear diagrams and cross-language examples. The Python modules documentation explains why Python developers often skip explicit singleton classes entirely. Modules are naturally singletons. Microsoft's lazy T documentation covers the idiomatic C# approach that gives you thread safety for free. Mark Seaman and Steven Vanderson's book on dependency injection provides the deeper theoretical foundation for why and how to replace singletons with injected dependencies. The Stack Overflow discussion captures the real-world controversy. It's one of the most debated topics in software design. Finally, Oracle's enum tutorial explains the Java language feature that makes enum singletons possible.